Hello friend, today we are going to learn the most basic algorithm, that is the binary search. Consider this is a 1,000-page book, which is a dictionary. If you want to find the meaning of the word sparrow, how will you look at it? Consider you are a dumb, foolish guy or girl. You might open the first page and start reading word by word and see if it has sparrow. In order to find the word sparrow, you might have to go across at least 800 pages. That would take you at least a day. As I know you are a very intelligent person, what will you do with this problem instead? You will just open the middle of the dictionary and see whether sparrow is in the left side or in the right side. If it is in the right side, you have reduced the problem into half. You don't want to look at this first 500 pages anymore. Your concentration is, your focus is only on the next 500 pages. You have literally half the problem that you have. Now, what will you do next? You will again take the middle of this 500 pages and see which side sparrow comes. Since it is in the left side, you don't care about what is there in the remaining 250 pages. So your only focus is on this 250 pages. Again, you will take the middle and see which side sparrow comes. It's in the right side. So you will leave out the remaining 125 pages and you will focus on this 125 pages. So you are literally reducing the problem into half in every step that you go about. You will be able to find the sparrow in this 1,000-page book within 10 lookups. If you don't have the word sparrow, that will also take only 10 lookups, because you will finally end up in one page which might or might not have the word sparrow. Instead of turning 800 pages, you have turned just 10 pages. See the difference. Instead of spending one day with this dictionary, you will have to spend only few seconds to find what you are looking for. See the power of binary search. If you are still not convinced or you don't feel the aha moment, let me give you something else. Consider, instead of 1,000 pages, you have 1 billion pages. Can you imagine a book of 1 billion pages? It's too big for anyone to read. Can you imagine how wide the book would be? It will be 100 kilometers thick. The book will be 100 kilometers thick. If you don't know what a kilometer is, it will be 62 miles thick. A book that starts here and ends 62 miles away. If you are going to go the dumb method, reading word by word to find the word sparrow, how much time will it take? I am sure you cannot get the sparrow in your lifetime. But if you use binary search, how can you reduce the problem? How can you reduce the time you take to get the word that you are looking for? You can guess and type it in the comment. Have you typed it in the comment? I believe you might think it will take at least a month or so, right? How many lookups? Few lakhs of lookups, right? That is what you might be thinking. But you are totally wrong. If you are right, I am happy. But the number of lookups to find the word sparrow in this 1 billion page book, which is 62 miles thick, is just 30 lookups. Can you imagine? A book that is 62 miles thick, if you want to find a single word from the book, from the dictionary, it will take just 30 lookups. Maybe you might need 30 seconds to get that word. See the power of binary search. See the power of algorithms. This should be the motivation for you to go ahead and learn each and every algorithm that exists. It's a fun topic. It's very interesting, it is intriguing, and it will blow your mind in every step you take. That's the power of algorithms, and that's the beauty of algorithms. Now let's implement binary search in the whiteboard. Make sure you have a pen and a paper with you and try to implement the binary search yourself as we go along. If you feel stuck, I will take you with me. If you are not stuck, I am very happy for you to complete the binary search without watching my video. Since I assume this might be your first algorithm that you are attempting, I would keep it simple. Instead of having a word, a string, or a dictionary, I am going to use numbers instead. You have billions of numbers and you are going to find one number. And the assumption is you have all the numbers arranged in ascending order, like the dictionary has all the words arranged in ascending order. Now let's implement the binary search algorithm. The assumption is there is an array ARR, which is an integer array which has many integers. Those are in sorted order. That is the assumption. They are in ascending order. Example 1, 5, 7, 11, 21, 32, 65, 70, 80, 92. When we are calling this binary search, we have to pass at least three arguments. One, the array itself, where you are going to look for the number. Then you have to pass the lowest index and the highest index. Why do you want to do that? Because as in the dictionary example, you have seen that it's not always the whole book. When you go to subproblems, you will end up in places like from 125th page to 250th page you are going to search. That time you cannot just send the array and assume that the function knows where to start and where to end. So we are writing a function that can solve the main problem as well as subproblems in the same way. So int binary search. Why integer? Because we are going to return the position of the number that we are looking for, if it exists. If it doesn't exist, we will return -1. By position, I mean the index in the array. Int ARR, we are going to pass the number we are looking for. It's nothing but X. Then we want to pass in the low and the high. First, we will leave some space. You will know finally why we need those space. Let's solve the problem as we solved it with the physical dictionary. What did we do? We went to the middle of the dictionary. So you are going to the middle index of this array. I will name it int mid. Mid is nothing but the average of low and high, the mean of low and high. Why? Because whichever range you take the mean, you will end up in the mid of the starting and the ending portion of that range. So it is low plus high by 2. There is a small mistake, I can't say mistake. In some situations, this would cause problem. We will look into it later to have our focus on the algorithm itself. When you go to the middle page, what will you look for? Whether The x is in the left side or is it in the right side? If x is less than the middle element is nothing but ARR of mid. Keep in mind, mid is not the number in the array but just the index or the position in the array, like the page number in your dictionary. If x is less than the mid, we can ignore whatever is in the right. So we have to take care only the left side of mid. What is the left side of mid? The left side of mid is nothing but from low to mid minus 1. We will return, we will call the same function for this subproblem also. Binary search. ARR, we are passing ARR, we are passing the number we are going to find x, we are going to send the range. Range starts from low till mid minus 1. Why did we pass mid minus 1 and not mid? From this condition, you know whatever is in mid is not equal to x. It is greater than x. So we want to check only till mid minus 1. Else, what if x is in the right side? X is greater than ARR of mid. Then we will look only from mid plus 1 till high, because we know till mid it's not there. X is greater than mid, so x is greater than the element in the middle. So we have to check from mid plus 1 till high. Return binary search ARR x mid plus 1 high. Why did we not pass mid? Instead, we passed mid plus 1, because we checked whatever is in mid is not equal to x, it is less than x. So we are passing whatever is in mid plus 1 till high. What if it is equal? Imagine you opened the mid of the dictionary and you found the word sparrow. Will you again split and see till you get a last page? No, you already found the answer. Why would you want to go further? You just return the answer. Return mid, because mid has, if x is not less than the middle element and not greater than the middle element, then it's absolutely equal to middle element. Did this complete the whole solution? We are missing a small part, but a very important part. That's why I have left some space here. You see, the only place we are returning something valid is here. Yes, here both the places we are returning something, but that itself calls binary search again. But here we have something concrete that is getting returned without calling any other function. But this returns only for the case where we find the word sparrow or we find the number x. What if the number is not there? When will we find the number is not there? We won't find it in the first attempt or the third attempt, only at the end when we have only one page in hand. That's when we will find the number is not there. So what is the condition of having only one page? That's nothing but having only one element in the array range that we are passing. So low and high points to the same position. So we don't have anything else to check. We are going to check that particular value, whether it is less than the number, greater than the number, or equal to the number, right? No, we need not check these. When we have only one number, we can check whether it is equal and we can just return minus 1 if it is not equal, but if it is 1, then we will return the position. If low equal to high, in that case, if x is equal to ARR of low, then we return low. Since we don't have space, I am writing it here. Else, if it is not equal, that means we have only one element in this range. We have the one final page in the dictionary and we don't find the word sparrow. So we return -1. So this is the final condition where we didn't find a particular number. So we can do some manual calculation to verify this works. So we can take this array. So the low is this one and the high is this one. And the number we are looking for is 13. So x equal to 13. So what do? We come here whether low and high are equal. No, low is 0 and high is 9, the index 9. So we come here, we find the mid is nothing but 9 plus 0 by 2, which is nothing but 4, as it is an integer. If it is a float, it might be 4.5. We use integers because indexes are not a fraction or a decimal. 0 1, this is 0 1 2 3 4 5 6 7 8 and 9. So this is the mid. Now we check whether 13 is in the left side or in the right side. So if 13 is less than 14, yes, it is true. So we call binary search again with low as the same. Instead of high, we pass in mid minus 1. Mid is 4, mid minus 1 is 3. So this is the new high. The new function comes, the recursive call comes, and again we are checking whether low is equal to high. No, low is 0 and high is 3. So we go here. What is the mid? Mid is low plus high by 2, which is 0 plus 3 by 2, which is 1.5, which is 1 for an integer. So this is the mid. Now what do we see? Whether x, which is 13, is less than 3 or greater than 3. So here 13 is less than 3. No, it's false. So 13 is greater than 3. Yes, it's true. So what do we call? We have the same binary search call, but instead of searching the whole array, we are going to search from mid plus 1 to high. Now the new low is mid plus 1, which is nothing but 2, the second index. So this is low and this is the new low and this is high. Now we again come to the new function call. Whether low is equal to high? No, 2 is not equal to 3. So we find the mid. So 2 plus 3 by 2, which is 5, by 2, which is 2. So mid is 2. So low and mid are same. Mid is 2. And we see whether, so the arrays, the range is only from this to this. Now we check whether it is to the left or to the right. 13 is less than 5. No. 13 is greater than 5. Yes. So we call the same function, but the new low should be mid plus 1. So the new low should be mid plus 1, which is 2 plus 1 3. So this is the new low. The new high is also that. I mean, the new high is same as the old high and it is in the third index. Now again in the new function call, now low is also 3 and high is also 3. So we enter this particular condition and we check whether 13 is that element. Whether 13 is 11, no, it's false. So we go to the else case and it returns -1. So that -1 comes here and that minus 1 is returned from the previous call. Again that minus 1 comes to the larger array, the previous call, and finally it returns 3 or 4 times that we have come across, and finally it returns the value minus 1 to the caller of this function binary search. Did you feel it is difficult? Absolutely not, right? This is so simple, but there is a catch here. This one will not work in certain cases because there is a limit to the integer. So for example, each language, I think, has around 4 bytes length for integers. So it's around 2 billion. If it is an unsigned integer, it will be 4 billion. If it's a signed integer, it will be around 2 billion. I'm not exactly telling the right number, but you can just remember it's 2 billion. What if the low plus high exceeds 2 billion? It will override the limit of integer and it will give a negative number, which will create a problem here, because we cannot have a negative index in an array, at least for C, Java, etc., and we will end up crashing the system. So we have to do it intelligently. We know that high and low are integers. It can be in the integer range, but when we add them together, it shouldn't exceed the range. So how can we do that? We can do by high minus low by 2. Whether this will solve the problem? High minus low by 2. When we expand this, what will we get? This is just a rough calculation. High minus high by 2 plus low by 2, which is high minus high by 2 is high by 2 plus low by 2, which is nothing but high plus low by 2. So we end up in the same number, but we are not directly adding the high and low, and we are subtracting this number from high. So high minus low is also a small number, and we will end up in calculating high plus low by 2 without actually adding them. So we can write it in a programmatic way instead of writing it in a mathematical way. High minus high minus low by 2. This is our final answer. Hope you loved this algorithm. I believe you have tried it yourself and implemented the algorithm. Even if you got stuck in between, you might have understood how this algorithm works as you watched this video. If this is the first algorithm that you solved today, or going to solve after watching this video, you are in the right place. Let this be your first step in learning deeper, getting a better salary, and having a great career in your life. Learning algorithms is going to change your life. Hey friend, are you still watching the video? Then I would like to give you a gift. I have created a free guide that breaks down the most common data structure and algorithm patterns. Instead of telling you how an algorithm works, this guide tells you when to use it. Do you find yourself wondering which data structure or algorithm to use in a particular situation? Then this guide is definitely for you. Grab the guide by clicking the link in the description. Until we meet the next time, this is Shivakumar aka Algo Shiva signing off. Bye.